All right, 15.1. We're taking a look today at another branch of mathematics. We talked back in chapter 5 about a branch of mathematics called number theory. Do you guys remember me naming it that? Well, there's another branch of mathematics called graph theory, and that's actually what we're looking at in chapter 15 is graph theory. And just like when we did talk about number theory, there are graduate courses in graph theory as well. Graph theory has a lot of concepts that you may not have encountered before, a lot of vocabulary, okay? So it isn't so much that it's difficult conceptually, but there's a lot of things that you've never seen before with the vocabulary here, okay? So what we're going to start with then is what it means for something to be a graph, okay? So a graph is a collection of vertices. Collection means that there's at least one of them. And edges. And an edge is something that goes from one vertex to another vertex. So the image that you might have from that description is something that looks like this. You've got some vertices. I promise they're about to show up. There they are. Look at all those vertices. And some or all of them are going to be connected. So maybe it looks something like that. That would be considered a graph. Now, that would also be considered a simple graph. So a simple graph is a graph in which no more than one edge exists between two vertices, and no edge exists from a vertex to itself. In other words, let me show you what you can't have. You can't have this edge and this edge. Okay, so there's not two edges between a pair of points. One and only one way to get there. Okay? And then the other thing you can't have is you can't have an edge that does this sort of looping feature. Okay? So get out of your mind right now that edges have to be straight, because they don't. This is not edges in that sense, okay? They do not have to be a straight line between something. But do keep in your mind that these are not allowed. If you have those images, the graph is not considered a simple graph. And if you notice the note at the bottom, every graph that we're going to work with in this chapter is going to be a simple graph. Okay? So all of our graphs are going to have this property of no sort of circular path to itself kind of thing going on, and no double edges between points. Okay? So you have in your mind basically what it means to look like a graph now, okay? Now, I will add in one other thing up here. You can have images that do this too. So I can have sort of like a triangular shape within the picture or a square shape. I can also have a shape that looks like this, where it looks like those two edges overlap, but the point where they overlap is not another vertex. That's perfectly allowed and okay. All right, there's still just 1, 2, 3, 4, 5 vertices. There's not 6. Even though those two edges sort of look like they're crossing there. And the reason is because, notice I could have done this. Whoops, hang on. This isn't the reason, but you could have drawn it this way, and you still have an edge between them, and it didn't have to cross over that one. Or you can sort of imagine like, you guys have been to Dallas before, where they have all the interstates all stacked up on top of each other. Right? If you look down from on top, it looks like they cross, doesn't it? If you were looking down from a plane. But if you're on those roads, you know that they don't, right? They don't actually hit each other. You can have that sort of image in your mind as well, sort of like this is a three-dimensional side of a picture, okay? All right. Here's an example. We're going to determine first how many vertices there are. Second, how many edges that this graph has. So to start with first, how many vertices do we have? There are 7 vertices, A through G. Okay. And then how many edges? Are there 7? I have 7 written down. Do you guys count 7? Okay, great. So there are 7 vertices and there are 7 edges. Now, we have another term that we're going to define, and that is the degree of a vertex. So the degree of a vertex is the number of edges that join that vertex. Okay, so imagine the point, and it's the number of lines or segments or edges, technically, that are extending out from that point. Okay, so we're going to take that same graph that we just had a moment ago, and I'm going to list all the vertices out right here. I had vertices A, B, C, D, E, F, and G, right? Okay, so I'm going to go back to my picture. At vertex A, how many edges are coming out of or going into vertex A?
2.
2. So we say that vertex A has degree 2. Okay. How about vertex B?
2.
That's also 2. C?
1.
That one's 1. D
2.
is 2. E?
3.
3. F?
3.
Also 3. And last but not least, G?
1.
1. Okay, so one of the things it said is using the graph, find the degree of each vertex. Period. Second thing to do. Then add the degrees together to get the sum of the degrees of the graph. So what is the sum if I add all of those degrees together?
14.
14. Now pause for a moment and take a look. The sum was 14, correct? How many vertices were there? 7. So what does it sort of seem like might be a good conjecture to make?
Vertices squared is 0.
Not squared, but you're close. Times 2. And it will be here in a moment that our number of vertices times 2 is going to equal the degree of what we would call the degree of the graph, or the sum of the degrees in the graph. Okay? So bear with me, we'll get there in a little bit, but I want you to bring that to your attention right here. Next one, so this is the one Tyler was talking about before class and making fun of the fact that it said isomorphic. I'm not sure why, but isomorphic graphs. 2 graphs are isomorphic if there is a one-to-one matching between the vertices of the graphs with the property that should say if. Sometimes autocorrect just doesn't work so well. If there is an edge between 2 vertices in the one, then there is an edge between 2 vertices in the other. So jot that down, and then we're going to do an example. All right, so this is the picture that you have in your notes. Example, and it says, determine whether the 2 graphs are isomorphic. If so, label corresponding vertices of the 2 graphs with the same letters. And then it does have this color issue here, and so if you don't have any colors with me today, just kind of, you have to draw, right, something different or whatever. This is the only one that we're going to deal with today that's got color issues, but color code the corresponding edges. And then it says, note, there is more than one correct answer for these sometimes. So when you get to this section in your book, there will be that same note to remind yourself that if you got a different answer than someone else, it doesn't necessarily mean that either of you is incorrect. Okay? So we would like to try and show that there is this correspondence. So even if we fail, we need to have some letters to try to make this work. Okay? So let's label this graph over here with some letters. So I've got A, B, C, and D. And we want to know is, clearly I've got to have the same number of vertices, do I?
Yes.
Yeah, I've got 4 vertices in each graph, so that's a good thing. And I have to have the same number of edges. There are, let's see, well, the one on the right's easy to count. I have 5 edges on the right. Do I have 5 edges on the one on the left?
Yes.
I do. Remember, when they overlap and there's not a point actually plotted there, it's not a vertex. Okay, so my edges, let me count them. This is 1, 2, 3, and then I have 4 coming this way and 5 down that way. So I do have 5. All right, so what I'm going to do next is I'm going to come over here and notice that the degrees are going to have to match. So let's start with point A. What is the degree of point A? 2. So if there is an isomorphism between these two graphs, it's going to have to be labeled at one of the places where there's a degree 2. So I have to put A either on the top or on the bottom, because the top and the bottom vertices in the second graph both have a degree of 2. Make sense? I also have to put the other point, which is D, that has a degree of 2, where I've got a degree of 2. And my only chance is to have A and D either where I've listed them or flipped, so that D is on top and A is on bottom. B and C both have degree 3 in the left graph, correct? And that's good, because the degree on the right graph has them both, those last 2 points, as 3s. So I'm going to put B and C in right here like this, realizing that I could maybe have written them the other way, and that may or may not be helpful or work, but I may have to switch them, and if I do, I will. Okay? So here's how you make a decision. It's this issue of color coding. So I have colors, and I'm going to show you what the idea is here. So, in fact, let me use the colors from here. All right, let's try that. All right, so I'm supposed to have a line that goes from A to B. Do I have an edge in the other graph that goes from A to B?
Yes.
Yes, I do. It's right here. So there's my first color coding. Those two, once it finishes drawing, those two correspond to each other. There has to be a line between A and B, and there is. I need another color. So let's go with, I'll do a pink. I'm supposed to have a line from B to C. Do I have a line from B to C in the other graph?
Yes.
Yes, I do. And there it is. I need a new color. Green. How many colors am I going to need? 5 in this one, because I actually have 5 different ones. With what we're doing next time, we'll only need 4. But all right, so D to C. Well, I've got a D to C. It's right here. Yeah. That's too close to what I did before. How about
Orange.
orange? I can do orange. Okay. I need one from A to C. And I have that one right up here. I need one more color. Burgundy. Okay, I'll do burgundy. All right, from B to D is my last one. It looks burgundy on my iPad. It's not projecting the same kind of color, but all right. So I was able to actually connect them so that they matched. Right, all of the vertices had the edges they were supposed to have, going to the vertices they were supposed to go to. Everything worked. If I had run into a problem and I hadn't been able to do this matching up business, I would have had to take a step back first to see, did I put the vertices in the right place? Okay, because I had some flexibility, right? When I put the B and the C in there, I said, let's try this. And I could switch them and see, okay, well, maybe I should have tried it the other way and try that. But if all the trials that you do don't ever end up giving you this sort of a one-to-one color scheming business, then you don't have an isomorphism. Here we do. So these are, in fact, isomorphic. It says, determine whether the graphs are isomorphic. So these are isomorphic. All right. We're going to talk about one more concept real quick. It's the idea of being connected. A connected graph is a graph in which we can move from each vertex of the graph to every other vertex along the edges of the graph. In other words, I can start at one vertex and I can arrive at any other vertex I want to simply by following the graph. Okay, following the paths on the graph. Kind of like the paths are sidewalks. I don't want to step on the grass to get there. I've got to stay on the sidewalk to get there. Okay? And, of course, a disconnected graph is one in which we can't. We can't stay on the sidewalk. We would have to actually get there some other way or not get there at all.
It's a good analogy for each one of them. It's a good analogy for each one of them. Not even definitions.
Yep, you can do it that way. Whatever makes sense to you is fine. And we'll answer the question, the first question asked about the next picture, and then we'll stop, okay? So the next picture, for those of you who are finished writing, I won't move my screen just yet. The next one shows a picture, and it asks you for a couple different things. The first thing it asks you, though, is the graph connected?
Yep.
And the answer is no. So here's my graph. I know I could put letters in everywhere, and I think, did I put them in your paper?
No.
No? Okay. We can put letters in everywhere, but the problem is that there are places along this where I can't do this, right? This right over here, this triangle, I can move in a circular way around my triangle, but I can't get out of that triangle and get over to the points over here. Okay? And the same thing with this little segment in the middle here that sort of looks like it's crossing over things, but it doesn't let me get out. So this, in fact, is disconnected. And we will answer the pieces about the components next time. All right?